Okay, so now we are in sort of the bonus lab. This is going to be where I'm going to introduce two things that's going to speed our algorithms up here a little bit. Okay, so the first thing, if you look at the Gauss-Seidel method, we have this loop. We have the while loop, but inside this loop here, this takes a long time to do. The reason it takes a long time to do, there's two main reasons. One, at this point, we're not leveraging any sparse stuff. None of this is leveraging like a sparse thing because none of these matrices are sparse or anything like that. Okay, so that's one of the problems. The other problem is that if we come up to this, the at operator it's not using interpreted code, it's using compiled C code, and we want to try to get something similar to that. So there is a package that does that. So let me come up here to our import statements. It's called ngit for just in time. So, from number import ngit. Okay, so we're going to run that. So by the way, I'm also no longer in Google Colab. I'm on my Jupyter Notebook because things work a little bit better for there. You can still do it on Google Colab. It just, things go a little bit faster on my Google Notebook, on my Jupyter Notebook, and also I don't have to worry about going over my RAM limits for the for Google Colab. Okay, so what I'm going to do is I'm going to implement this as a function. So I'm just gonna make a couple of changes at a time. So this is called the sweep. So I'm gonna do so this is Gauss-Seidel sweep, and what it's gonna do is it's gonna take in A, B, and X. So it's basically gonna be the thing that does the update. And here's what it does. In is equal to length B. And then for I in range, we're just going to do exactly what we had. Okay, so in fact, all we're doing now is just writing this. So the only change we're doing now is cosmetic. So this is purely a cosmetic change at this point. So this is the sweep, and instead of having this here, it's just going to be here. So what I mean is the following. I'm going to call this GS3, and down here, instead of saying in this while loop, what we're going to have instead of all of this right here, we're just going to have the following. We're just going to say X is equal to GS sweep. And then we're going to give it A, B, and X. And everything else is going to remain the same. Okay, so in other words, again, nothing should change. So I'm going to go back to 100, and I'm going to look. I'm not going to do GS3 yet. I'm going to do GS2. Oops. Yeah, there we go. Okay. So, again, I haven't made any changes. I only ran the GS2. If I run the GS3, all of this should basically be the same, though it should take a little bit longer because we have all of these function calls. But it still should be 13,756 iterations. Again, I think it was a little bit longer, but though I don't know. Anyways, so what can we do to make this faster? So what we're going to do up here, we're going to do @njit, and what this means is it's going to compile this function, and then the first time you run this cell, it's going to compile this function, and then after that, it's going to just use the compiled code rather than the interpreted code, which should speed things up a little bit. So notice it's 0.797. That's how long it took. Everything else should be the same. All of the number of iterations should be the same. the error should be the same. All that should be the same. But either this time or the time after this, it should be a little bit shorter than 0.797. Okay, so 0.30, 0.13. Okay, so we can see it's significantly faster simply because we have said we're going to, compile this code first rather than interpreting it each time. And this actually lets us probably scoot this up to 500 a little bit. Yeah, so it's just like using this NJIT thing is going to let us sort of get some of the advantages that exist using these built-in @ operators and stuff like that. Okay, I did not expect it to take this much longer now. Okay. So this is the first thing that we can do. I'm just going to, okay. So, 27 seconds. Again, still 11,000 times as long as NumPy. So, this is 1,300 times for n is equal to 100. Okay, so still our little Gauss-Seidel method here is not beating NumPy. In fact, it's a lot faster than, it's a lot slower than NumPy. But let's see if we can make some of this a little bit better. Because notice up here, we're still sort of doing a very dense matrix vector multiplication. We're still, looping over everything and stuff like that. Let's see if there's a way we can use sparse stuff to make this go even faster. And so here I'm going to introduce some of the SciPy sparse ideas. So m is the matrix. So I'm going to come up here. I'm going to set m equal to 5 or n equals to 5. So if we come down here, I'm just going to do some experimentation. So I'm going to print m. Okay, this is exactly what we expect it should be. And now I'm going to introduce, like I said, I'm going to introduce some sparse ideas. How we can make this matrix vector multiplication, or how to make this loop faster using sparse ideas. And this is just one way we can do it. Okay, so we're going to first get a sparse version of our matrix. So we want a compressed sparse row matrix. Okay, so what is this? So I'm just going to, I don't know exactly what this is going to print. Oh, M, not A. And this is going to be M. Okay, so notice what this prints. So these are the values, and these are the coordinates. So it says at coordinate 0, 0, first row, the 0th row, 0th column, there's going to be a 2. Then it says at 0th row, first column, there's going to be a -1. Then it says it's going to go to the next non-zero entry, and it's going to say at the first row, 0th column, there's going to be a -1, and so on and so forth. Okay, so this is how it is storing the matrix. Or this is actually not how it's storing the matrix. This is how it's printing the matrix. How does it store the matrix? Well, there are going to be 3 different, so the data structure to store a sparse matrix, the way it's storing a sparse matrix, there's 3 different arrays. There's going to be the data array. So I'm going to say data is equal to m csr.data. Okay, so we're going to print this. Notice what it's printing. All this is, if we start, if we read row by row, left from right, top to bottom, that's exactly what this is. 2, -1, -1, 2, -1. And it doesn't have the zeros. That's the whole point. So that's exactly what this. That is the first row. That is the second, or let me back up. That is the 0th indexed row, the first indexed row, the 2 indexed row, the 3 indexed row, and the last indexed row, the 4 indexed row. Okay, so that's the data. And then there's going to be another thing. There's going to be the columns. So columns is going to be m csr dot indices. Now what this is going to do, is going to give us the column of each one of these data points, of each one of these data. So like that, the column of that entry is 0, the column of that entry is 1, the column of that entry is 0, the column of that entry is 1, the column of that entry is 2. Then we're going to have 1, 2, 3. then we're going to have 2, 3, 4, and then 3, 4. So that's what it's going to look like, and that's exactly what we get. So it says the column of this is 0. The column of that is 1. The column of that is going to be, is that minus 1 right there? That's going to be 0. If we come down here, what is this last one? The last column is 4. That minus 1 is going to be the third column. So that's what that is. Okay, so there's 3 different arrays. One has the data. One has the indices of the columns. So you would think that the other one is going to be the indices of the row. That would make perfect sense. But it's not. And it seems confusing at first, but it's actually pretty cool. So the rows, I'm going to call it row pointer, and you'll see why, is going to be mcsr.indptr. Okay. I want this to be ptr. Okay. And then what we're going to do is print row ptr. Okay, so what this is, it's going to be an array. It's going to be an array of length 4. Actually, it's going to be an array of length 5. And the zeroth indexed entry of row pointer is going to be the element of the data vector and the element of the column vector that corresponds to the first entry on row 1. Or on the 0th indexed row. Okay. Row pointer 1 is going to tell us which one of these elements is the first element in the 1 indexed row. Row pointer 2 is going to tell us which one of these entries is the first entry in this 2 indexed row. Okay, so if we look over here, which one of these entries corresponds to the first non-zero entry in the 0th indexed row? Well, it's going to be 2. So let's figure out what row pointer is going to be. So 0, this index right here is the first element in a 0 indexed row. So the 0 index of row pointer is going to be 0. Okay, now which one of these corresponds to the first non-zero entry in the 1 indexed row? So that's this row right here. It's going to be that minus 1. So that is on the first row, or sorry, that is on the 0 indexed row. That is on the 0 indexed row. That is the first one on the 1 indexed row. And it is the 0, 1, 2 index of that. Okay? What about the 2 indexed row? What is going to be the first element here in the 2 indexed row? Well, we're going to have go 2 minus 1. Those are the 0 index row. Minus 1, 2, minus 1, that is the first index row, the 1 index row. That minus 1 there, that is the first entry in the 2 index row. And it is the 0, 1, 2, 3, 4, 5 index. Okay? Okay, this is the third entry. That is the third indexed row. The row that has index 3. Okay, so which one of these corresponds to that minus 1? Well, we've got 2 minus 1. That's the first row. That is the 0 index row. That is the 1 index row. That is the 2 index row. This is the 3 index row. So 0, 1, 2, 3, 4, 5, 6, 7, 8. So we're going to have 8. Okay, this is the 4th indexed row. Okay, so this minus 1 is the entry in data corresponding to the first non-zero in the 4 indexed row. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. This is going to be 11. And the last entry is going to be the last, it's going to be where the last row ends. So it should be 12. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. So hopefully when I run this, row pointer is going to be that array right there without the commas, unless I made a mistake. And I have. What was my mistake here? So this is okay. So this right here is the first, that is the first non-zero entry of the one index row, and it is the index 0, 1, 2. So that one should have been a 2. Okay. Other than that, everything else is fine. Oh, and sorry, 13 is one index more than this last index. Okay, so how is this going to help us? So we have, this is the data structure that we're going to use. Okay, so what we're going to do then is we're going to come back up here, and we're going to use that to make a new sweep method. So df gs sweep 2, and what is this going to take in? It's going to take in a data array, the columns array, and the row pointer array, and then b and x. Okay, so n is going to be equal to the length of b. Excuse me. Now what we're going to do is the following for I in range n. Okay, so we're going to go through. We still have to go through each entry in x to do the following computations. And we're going to say s is equal to 0.0. This is what we're going to be adding. It's going to be like our x plus equals s is what's going to end up happening. Or x of I plus equals s. Then we're going to say diag is equal to 0.0. And now what we're going to do is the following. For k in range, row pointer I to row pointer, oops, wow. Okay, for these values, we're going to do something. So what are we going to do? Okay, so remember what row pointer I is. If we come down here, like if I is equal to 1, we're going to look at this entry here too. So row pointer of 1 is 2. Row pointer of I plus 1. If I is equal to 1, row pointer of I is 2. Row pointer of I plus 1 is 5. So we're going to look in the range 2, 3, and 4. Okay, this means if I come up here, what does this mean? So 0, 1, 2. These the entries so what this is saying is that row the first index row starts at -1, and and row index index 5 is going to be the next row. So then range 2 to 5 means indices 2, 3, and 4, because remember the range doesn't take that the last index isn't included. So if we're looking at this example here and I is equal to 1, it's going to say row pointer of I is equal to 2. Row pointer of I plus 1 is going to be 5. So range row pointer I to row pointer I plus 1 are going to be the indices 2, 3, and 4. And that says that indices 2, 3, and 4 of this data are going to correspond to the one index row of the matrix. So that's going to be these right here correspond to the one index row. Now, when we do the matrix vector multiplication, we need to know what column they're in to multiply by the appropriate entry of our vector. Well, the data entries, indices 2, 3, and 4, are going to be the columns of these. So the row is equal to I, which in this experiment, I is equal to 1. The row is equal to 1, the one index row, which is this. And the columns are going to be these columns right here. So what it says, if I is equal to 1, it says that in the row where the index is 1, that's going to be this row right here. In the columns with indices 0, 1, and 2 are going to be the data -1, 2, and -1, which is exactly what we have here. Okay, so let's come back up here. Okay, so then what we're going to say then is S plus equal X columns of K, okay, times data. Okay. This is the entry of the matrix. This is the corresponding column of the X of the vector we're doing the product with. Okay. Now we need to do something special here. So we need to divide by the diagonal. So the diagonal is going to happen if we're on ith row. is going to be when I is equal, so if row is equal to the column. That's what that says. Diag is going to be equal to data k, like this. Okay, so think about what's going on here. This is really cool. Okay, and then we're going to say xi plus equals 1 over diag times b of I, b of I minus s. Okay, so everything here looks proper. That's at the right level. Then we're going to return x. Okay, I'm going to make a GS4. And now the only difference is down here. We got to make this a little bit different because when we pass in the sweep thing here, it's not just going to be a, b, and x that we pass. It's going to be the data, the columns, and the row pointer. Okay, so now I'm just going to copy and paste some stuff because I'm getting tired of typing. Getting a little bit lazy. All right. Whoops. I don't know why it's not tabbing properly. So then we're going to do data, columns, row pointer. Okay. I'm going to try this out on a matrix of size 10 just to make sure everything is running properly. Okay, I'm going to do it with a matrix size 10 with the old one just to make sure everything here is working properly. Okay, so 1.08. Now let's look at, 108. Let's look at GS4 now. Ay. Expected 3, got 5. Oh, because I didn't change this GS sweep 2. Okay. Why did it take 4,000 iterations? Well, that's not good. Something is definitely wrong here, because it's taking the maximum number of iterations. So where did the error come from? Oh, b of I minus 2 instead of s. Why did I do that? Okay, there we go. Okay, so now let's see what happens. Let's go up to 100. Now again, the number of iterations for these methods is going to be the same no matter what, because it's the only thing that we're changing is the implementation of the matrix vector multiplication, and that's just from the iterative methods point of view. That's a black box, and it's not going to change the number of iterations needed. But okay, so let's look at this. N is equal to 100. Takes 1.09 seconds, 8,000 seconds, or sorry, 8,000 times faster than NumPy, or 8,000 times slower than NumPy. One thing that I want to compare it, I'm going to get rid of this. Okay, so let's do a comparison here. Okay, if I run this, that's about a second, about a second. Okay, so now let's look to see what happens when I do the GS3. This does not have the sparse implementation. So, and I've taken away the fact that this is going to be sort of compiled code. So I'm going to run this a couple of times. Okay, the first one doesn't count. Wow, so it's still faster, which doesn't make sense to me right now. I think probably because of the function calls. If we go up to 500, let's try 500. Sorry, now you just get to watch me experiment. Okay, well, this is exhilarating TV. I'm surprised it is taking this long to run. Oh, man. Well, this is annoying. Sorry. Okay. I'm just gonna stop it. Let's go. Let's try it. Let's experiment with 200. Okay, so using the Gauss Seidel, where the sweep is not implementing sparse things, it takes 6.6 seconds. I'm gonna try that one more time, so we shouldn't have this at more than 10 seconds this time. Just want to get a couple of values. Yeah, 6.6 again. Let's look at GS4. Let's see if this is going to get down below 6.6. But notice they're both taking the same number of iterations. Okay, so this is a little bit slower, but the ratio is not as extreme as it was before. Okay, so what we're going to do is we're going to do this on this one as well. Okay, and now it took, note 60,000 iterations, 9.6 seconds. This first time you run it, look how much faster it's going. 0.57 seconds. Okay, so, it really, really makes it go faster when we do this pre-compiled code. And now let's just compare. Okay, we got 0.58 seconds. Let's look at the other implementation. Okay, so now it's a little bit faster. So now the sparse one looks maybe a little bit faster. Okay. All right. So what we see here is by really leveraging the fact that we have sparse matrices up here. Okay. By the way, you can also do the matrix vector multiplication this way as well. By implementing the fact that we have sparse matrices up here in the sweep function, and also doing the pre-compiled thing, we go from from a lot of seconds to 0.88 seconds. So in this setup, we have 0.88 seconds. If we just do the very easiest Gauss-Seidel method, the very easiest component-wise Gauss-Seidel method, let's see how long that takes. I think it's going to take quite a long amount of time. Okay, so 6 seconds. So 6 seconds for this, and then okay, so it's 10 times faster right now. Simply because we haven't changed the iterative method, we've changed the implementation of the matrix vector multiplication. So you can see that this makes a significant difference, right? I mean, a factor of 10 is the difference between a simulation taking a coffee break to run or a lunch to run, or the difference between a simulation taking a lunch break to run and like an overnight to run. Okay, so but the iterative method has stayed the same. You can see this is the same number of iterations each time. It's just we have more cleverly or more efficiently implemented the matrix vector multiplication. And of course, if you're just working in one specific domain, you could have an even more specific matrix vector multiplier that could go even faster. But again, the iterative method hasn't changed. Okay, the number of iterations is the same, but practically it's important which matrix vector how we implement the matrix vector multiplication. Okay, so now let's come down here to the SOR. What I'm going to do is I'm going to modify these. let's see. Let me make sure I'm going to do this properly here. What I'm going to do is I'm simply going to modify these two things right here to make it work in the SOR context. So this is the SOR, right? Because the SOR is very similar to the Gauss-Seidel. So I'm going to call this GS sweep SOR. It's going to take data, columns, also W. Yeah, okay. So the only difference, the only difference that we need to make here is that for this part right here, just like above, we need to multiply it by the relaxation parameter W. That is the only difference we have to make. Okay, so it's great. And then if we come down here, the only difference that we need to make is that we want to do the SOR GS sweep. Okay, so again, let me just run this. Let me just run this. I haven't even changed anything yet. 333. Okay, so now if I come up here and do, I'm going to call this SOR2. Okay, if I come up here, SOR2, where are we? SOR2. Okay, so when I run this, I want to see how long it's going to take. Now, of course. Oh, because down here, I need to include the W. Okay. Let me make sure I got this in the right order. Data, columns, row pointer. This is a hard one for me to say. All right. Oh, it takes 4 positional. Oh, because I haven't given the W up here yet. Okay. Let me make sure I have this in the right order when I call it. MBW. Yep. Okay. Okay. Awesome. 333. Very good. 0.07 seconds. Wow, that was not long at all. So let's compare it. If we just do SOR, this is 0.04. This is still going to be a little bit longer. Okay. It's going to be a little bit longer because there's some overhead that's not really letting us see the asymptotics yet. So let's see what happens when n goes to 500. Okay, before it took a long time for n equals 500. Okay, so let's do n equals 500, 1800 iterations. Very good. And notice the ratio. This is saying that our method is taking 55 times as long as the NumPy method. Let's look at 1,000. Okay, now the ratio is down to 36. Okay, that's getting pretty good. What about when we go to 5,000? I think when I was not recording it, it was not taking it nearly as long. I think because I'm recording now, things are taking longer to run, like embarrassingly long to run. I don't know why it's taking so long to run. I really don't. Well, I think it is just because I've got OBS running as well, and that probably takes a lot of resources. Okay. Wow. Okay, sorry about that. So I don't. Man, this is one of those things that I am disappointed because when I did this before, uh, I got much different results than what I'm getting now. Why is it not doing what I want it to do? So something I have implemented something wrong over here, and I can't figure out what it is. So hold on. Now we get to debug what I've done wrong over here. Okay. Let's see, is the error? Yeah, okay, so everything is happening here like it should be. Oh, yes. Here's the issue. I forgot. So, what is this error here going to be? Well, it's going to be very small. When n is equal to 5,000, this is going to be like within machine precision, which is what we have here. So what we're going to do is we're going to change our error here to the following: max of this or 1e12. Let's see what happens now. Still not exactly what I wanted to have happen. I am a little bit confused now about what's happening. Man, nothing is making sense now. Why? Ay. Why is it like this? Okay, so I have implemented something wrong here, and I cannot figure out what it is. Oh, one thing that is not good. I think this is the issue. For this residual right here, we really don't need to compute it every single time. So let's just compute it for every 100. We're just going to compute this for every 100, and let's see if this speeds things up a little bit. This was much less dramatic than I thought it was going to be. I spent So much time coming up with examples to demonstrate the things that I wanted to demonstrate, and it just is not doing what I want it to do. Ah, man, yeah, I really think it's because this OBS is running that is also making this take much longer than it should. But I really don't get it. Like, I can run it in a notebook that I have off of screen that it does not take as long to do. Yeah, so I think you're just going to have to do this on your own computer. It's probably best if you do it in Jupiter. I don't know. This is so crazy to me. Like when I run this on another notebook that I have open, it's taking this 6 seconds to run, not 70 seconds. So I really don't know what the difference is. Um, yeah, I do not know what the difference is. Um, okay. Anyways, so here's what I suggest. Do what I've done here. Run it on your computer, and you should get things that are much faster. And as a matter of fact, the ratio should be to like one half. In other words, our method should be faster than the NumPy method, which I wanted to illustrate. I wanted to be able to show you that on the video, but it's not working. Anyways, do that. And well, so now what we've done, the first video I made, we saw how to implement these iterative methods, and then now we looked at different ways where we could implement the matrix vector multiplication to get things that should be faster, much faster even than they are now. Okay, that's going to be it for this video.